Energy Practice Worksheet. Question number 1. Determine the kinetic energy stored on the card with a mass of 200 kilograms if it is moving at a velocity of 25 meters per second. Let's start by getting the givens. It says the mass of the card is 200 kilograms, so that's M. M equals 200 kg. Kg stands for kilograms. And the other thing is V, the velocity, which is 25 meters per second. There's nothing else given there. Now, what is the unknown? What are they asking us? They're asking us for the kinetic energy of the car. That's our question mark. And the equation for kinetic energy is on page number 3. And it says it's half the mass times the square of the velocity. Let's put it this way. Right? So this is an easy problem. All you need to do is just plug the numbers in. The mass is 200 kilograms. How much is half the mass? Half of 200 is 100. 100 kilograms times parenthesis 25 squared, which is the same as 25 times 25, and that will be meters per second times meters per second, because you multiply both, right? Okay, let's put it the right way. It's going to be 25 meters per second times 25 meters per second. Alright, and now we solve. So the kinetic energy equals, so when we do this, we start by getting the square of the number, 25 times 25. So I'm going to apply the calculator here, which is get the square of 25, or just multiply 25 times 25. And I get 625, and then I multiply that by 100. And you're going to get 62,500. Okay, 62,500 joules. And that is the kinetic energy of that car. Right? That's it. For number 1. For number 2, okay. Let's go in here. Determine the potential energy stored on a 20 kilograms bowling ball before being dropped from the top of the Leaning Tower of Pisa in Italy. If it is known that its height is 55.86 meters. So again, let's get the givens. So you see the mass of the ball is 20 kilograms. What else is given? The height of the tower is 55, so remember H, right? It's 55.86 meters. And the other thing that is given that we need, even though it's not written down there, but it's given because it's something that we should know about, is the acceleration of free fall, or G, which is meters per second squared, or meters per second per second. And we need to find the potential gravitational energy of the ball at the top of the Tower of Pisa. The equation for potential energy is mass times gravity times height. So all we need to do in substitution, right, is plug in the numbers. 20 kilograms times 9.8 meters per second squared times 55.86 meters. Alright. And when you multiply the 3 numbers together, you're going to get a number which is equal to, let's see, just pull out the calculator here, 20 times 9.8 times 55.86. That's giving me a total of 10,948.56 joules. ball at the top of the top. That's how you do number two. And let's go over number three. Number three says a bear of mass equal to 150 kilograms is standing at the top of a hill. The potential gravitational energy stored on the bear is 50,000 joules. Determine the height of the hill. Okay, let's write down the givens. This is the mass of the bear is 150 kilograms. It's a big bear. It also says that the potential energy stored on the bear, right, is 50,000 joules. And also, we have to pull our gravity because we're going to need it. 9.8 meters per second per second. What is the unknown? It says determine the height of the hill. So h is our unknown. So when we use the equation for potential energy, which is mass times gravity times height, the goal here is to find h. Okay, so you can either rewrite the equation for h and then plug in the numbers, or plug in the numbers, simplify, and then write the equation for h. Either way, it's okay. So what I mean is, okay, well, if you want to solve for h, you divide the whole equation by h. Sorry, by mass times gravity. It's going to be better this way, right? And then you're going to get mass times gravity divided by mass times gravity times h. And you can see that these guys over here, they strike up, they simplify, right? So the height h is equal to the potential energy divided by the mass and multiplying the gravity. So you can rewrite the equation here as PE divided by mg. And now we can plug in the numbers. PE happens to be 50,000 joules. And you divide that by, and you can open parentheses here, 9.8 meters per second square times the mass of the bear, 150 kilograms. And so you multiply the numbers in the denominator, and then you can reduce the equation so you can divide. Okay, so this is going to be 50,000. Oh, come on. Joules over. Let's omit the units for now, because at the end I know it's going to be meters because it's a distance, right? We're using metric units, so the height should be in meters. So if you multiply 9.8 from the calculator here times 150, you get 1,407, right? So you're dividing 1,000 by 1,407, and whatever you get is going to be in meters. Okay, so let's do it. So it's 50,000 divided by 1,170, and we get 34.0136. We can round it to 34. So this is 34 meters. That's how high the hill is. And we're done. All right. So for number 3, then we have number 4. And number 4 says a 20 kilograms baseball has a kinetic energy of 4,000 joules. Determine the velocity of the baseball. Okay, so they give us the mass of the baseball. It's 20 kilograms. That's a heavy baseball. Okay, and the kinetic energy of the baseball is 4,000 joules. We need to determine the velocity, v, right, of the baseball. And we're going to use the equation for kinetic energy, as it is in page number 3, which is 1/2 the mass times the square velocity. Now we need to solve for v. So in order for us to solve for v, we first need to solve for v squared and then get the square root of v. Alright, so rearranging this to v squared, what you do is you multiply by 2 divided by m in both sides. You get ke times 2 over m will be equal to v squared. Let's simplify the other side. So let's solve for v squared first. So that would be 4,000 joules. Let's omit the units. Let's just multiply and divide the numbers, and then let's see what we get. It's going to be in meters squared per second squared. When you get the square root, it's going to be meters per second. Times 2 divided by 20. Okay? That is 8,000 divided by 20. Correct? So 8,000. Why 8,000? Because it's 4,000 times 2. 8,000 divided by 20 is 400. So you get 400 meters squared over second squared. So how do you get v? Well, v will be equal to the square root. You can put it this way in Google Documents of 400 meters squared per second squared, which is going to give you the answer in meters per second. So what's the square root of 400? Do we have that feature here? Oh, yes, we do. So if you use the square root, you get 20. So this is 20 meters per second. And that's how you do it. So what is the complication here? The complication here is that the velocity is square, so you're going to have to use the square root at the end. Okay? But it's not big deal. You can do it. Number 5. All right. Number 5 is using basically the law of conservation of energy. And you can see that there's a 10 kilograms car moving with a velocity of 20 meters per second, and it's about to go up a hill that is 20 meters high at the very top. All the initial kinetic energy of the car converts to potential gravitational energy. Here is the conservation of energy. Will the car reach the top of the hill? Well, for that we need to know how high it can go with this 20 meters per second. All right, so first we're going to find the kinetic energy of the car, and the kinetic energy of the car converts to potential energy of the car, and then we can solve for the height and see how high it can actually go with this 20 meters per second and this mass of 10 kilograms. All right, so the givens are the mass. Mass is 10 kilograms, and the velocity of the car, which is 20 meters per second. And then we need to find the kinetic energy in this side. So we're going to use the equation for kinetic energy, which is half the mass times the square of the velocity. All right, and the kinetic energy will be equal to, okay. If the mass is 10 kilograms, half the mass is 5 kilograms. 5 kilograms times 20 meters per second square. 20 meters per second square. If you look at what we did in the previous exercise, you can see that the square root of 400 is 20, which means that 20 squared is equal to 400. You don't even need to use a calculator to get the square of 20, but if you want to do it, 20 squared, 400. All right. And that number times 5 will give me the kinetic energy, which is 2,000. So the kinetic energy here will be 2,000 joules. And that is the amount of potential energy that the car can get. Okay? So, because it says in the problem that the initial kinetic energy of the car converts to potential gravitational energy. So that means that all these 2,000 joules of kinetic energy will be converted, or will be turned into potential energy as the car goes up the hill. The car will have 2,000 joules of energy available to go up the hill. And let's pretend that this is placed on coasting, so the engine is not doing any work on the wheels at the time this happens. So all the energy of the motion can convert into energy of the height, right? So now that we have the potential energy, it is a given in the second part of this. So it is 2,000 joules. We have the mass of the car from the problem, 10 kilograms. And we have G, which is 9.8 meters per second squared. We need to find the height that car can go. We're going to use the equation for potential energy. Mass times gravity times height. And we're going to solve this for the height, which is the potential energy divided by mass times gravity. Check your algebra. Alright, so we can find the height as 2,000 joules divided by, let's omit the units, let's put it at the end. We know it's going to be in meters. And then we have to multiply 10 times 9.8, which is 98. So we don't really need the parentheses. Alright, so it's 2,000 divided by 98. And what we get will be 8 meters. So 2,000 divided by 98, which is 9.8 times 10, right? 20.41, right? Rounded. 20.41 meters. And I want you to look at that number and then tell me if that number is sufficient to go up the hill. The hill is 20 meters high. The car has enough energy to go 20.41 meters. Will the car reach the top of the hill? Yes or no? Write down your answer over here. Okay? Just compare the numbers and get a conclusion about it. Of course, it will be able to go up the hill theoretically. If there's any loss of energy due to air resistance and friction, it won't happen because the numbers are too close. But theoretically, in an ideal case, it should be able to go all the way to the top of the hill. Okay, so let's go to number 6. On number 6, says determine how fast a 1 kilogram ball will move after being pushed by a spring-loaded rifle of spring constant K equals to 89 newtons per meter, and that was initially compressed a distance of 30 centimeters or 0.3 meters. Right, so we're gonna use the same principle here. All the energy stored in the spring will be converted into kinetic energy of the ball, so we can find how fast the ball is moving. So first we're gonna find the potential elastic energy that will be equal to the kinetic energy, and with that number we can solve for V. V squared first, then V. Okay, so let's put the givens here. We have the mass, but we don't need the mass of the ball here. We can put it on this one here. Right? we have the mass of the ball, which is 1 kilogram. We have the spring constant K, that one goes here, which is 80 newtons per meter. And we also have the stretching distance X, which is 0.3 meters. And they're asking us for the elastic energy of the spring, because that will be equal to the kinetic energy of the ball eventually. All right, so we're going to pull out the equation for elastic energy, and that's going to be half the spring constant times the square of the stretching length. All right, so plugging the numbers in, half of K, well, how much is half of 80? That would be 40, and we're going to put the units, just the numbers, times 0.3 squared, so 0.3 times 0.3. All right, and that is our number. So we're going to multiply these numbers together, and we're going to get the answer. So 0.3 times itself is 0.09 times 40, 3.6. So we have 3.6 joules stored in the spring. All right. So that energy is the energy available for the ball. So the ball will have a kinetic energy, and that's a given for the second part of this problem, which is equal to 3.6 joules. All right. So we need to find how fast the ball is moving. So for that, we're going to use the equation for kinetic energy as half the mass times the square of the velocity, as we did before on the previous problem. We solve for the square of the velocity first, which is going to be 2 times the kinetic energy divided by the mass of the ball. And then we get a square root. So v squared, it is 2, let's use parentheses here. We've got 2 times 3.6, all that divided by 1. And whatever we get, that will be the square of the velocity. So how much is 2 times 3.6? Well, 3.6 times 2 is 7.2. Divided by 1, 7.2. So we get 7.2. Remember, this is in meters square over seconds square. And now we can get the velocity as the square root of 7.2. And that will be given in meters per second. So how much is the square root of 7.2? Right here. So I'll just get the square root. I get 2.68 round. Okay, so 2.68 meters per second. And that is the answer for this problem. So the ball will be moving at a speed of 2.68 meters per second. This number too red. So let's lower it. There. Okay? And that is how you do it. Okay? Using conservation of energy, you need to find out the elastic energy on the spring. Also, assuming that all the energy on the spring is being passed to the ball, is used by the ball to move, and then that's stated here, then we can calculate the final velocity, which is the velocity of the ball after it's being chopped. Okay, and that's it. That's all. Thank you for paying attention.